So we're actually going to talk in a little bit about like certain tells in a function and which ones are growing faster than others when you're comparing them. So if you see an exponential in the denominator, it's going to outpace a polynomial, right? Because remember, and that's the whole cool thing about this is all the limits we're looking at are all going to infinity. So there's a lot of neat stuff that happens when numbers get really big and they're really predictable. So for this guy, right, we can clearly see converges to 0. All right, and let's look at the last function sequence we looked at in our first example yesterday. And this was the one we defined recursively. So we said, well, D1 was 25, but the next term is by taking the previous term and subtracting 5. So we saw when we did this sequence that, right, we started with 25, then we took away 5, and we kept doing this, and we eventually crossed 0. And we said that that's okay if you cross 0, but this thing's just going to keep now growing in the negative direction. So just like the sequence that was 2 and 4, it's really hard for me to set up a limit to evaluate this, right? Because you just keep looping and looping and looping with the equations. So if you actually line out this sequence, it's very obvious what the limit of this is, right? If you look at these terms as we keep going up to going out as n goes to infinity, the numbers are getting really, really big negatively. So the limit of this is going to negative infinity, right, as n goes to infinity. You can just see it happening. It's just going to keep plummeting down to negative infinity. So if the limit doesn't exist, right, we say the sequence diverges. Yes, so the question is, right, since this one doesn't go to positive or negative infinity, but the limit didn't exist, yes, we would conclude that A sub n diverges. Okay, so what I like about these 4 limits is 2 of them required L'Hopital, right? One of them, there were 2 different ways to do it, right? 2 of them diverged, but they diverged in different ways. One diverged because it just kept bouncing between 2 values, so the limit didn't exist. The other one diverged because it was blowing up to negative infinity. Okay, so don't forget, infinite limits are just special cases of does not exist. All right, so then there's actually another type of sequence where it doesn't fit in any of these categories, right? So do any of you guys remember the squeeze, or some people call it the sandwich theorem from Calc 1? So we're going to look at that. So one of the things I do enjoy about the section in sequences is we really do get to go back into Calc 1 and grab all this stuff that we did that we were like, why the hell did we do any of this? And actually see there's a real world, like, actual valid reason you have to know how to do these limits. All right, so the squeeze slash sandwich theorem, it kind of depends on who your teacher was. So let's look at it the traditional way. So we have 3 functions, f of x, g of x, and h of x. And they have the relationship that g of x is always less than or equal to f of x, and f of x is always less than or equal to h of x. And this is true for all x. So one of the things we learned about this theorem was if this is the order, right, of these 3 functions numerically, that any value you put in, g of x will be smaller than f of x, and f of x will be smaller than h of x, right? And what we mean by that is the same value of x, right? So g of 2 is less than or equal to f of 2, which is less than or equal to h of 2. So taking the limit of an inequality actually preserves the order of the inequality. So what we said is, well, the limit as x approaches a of g of x must be less than or equal to the limit as x approaches a of f of x, which is less than or equal to the limit as x approaches a of h of x. And so what we used this for specifically was, imagine if f of x was a function that was constructed in such a way that we just couldn't algebraically take the limit, or we just couldn't see, right? L'Hopital didn't get us out of it. We maybe had an alternating component in it. We just couldn't really see what was going on. So where the squeeze theorem is useful is it says, well, if you can find a function that's always bigger than f of x and a function that's always less than f of x, whose limits we can compute, right? So the added kind of little special caveat here was, well, if the limit as x approaches a of g of x is equal to the limit as x approaches a of f of x, right? They equal some value L, well then f of x must be L as well. So you literally sandwich your function in between two other functions, and if the limit on the right is 0, right, and the limit on the left is 0, and f of x always lives between those two guys, well then it has to squeeze through, and its limit must be 0 as well. And so that's when we use this. Does anybody remember kind of what kind of functions that we kind of like use this a lot for? No? All right. Trig. Think about sine and cosine. They're in the numerator, right? Well, they always bounce between two values, and it's really hard to find the limit, right, of when you have sine or cosine in the numerator if the value doesn't quite accept. So if I'm taking the limit as x goes to 0, right, that's a known value. I can plug that into sine and cosine all day. But what if I want the limit as x goes to infinity? How do you know what to do with sine or cosine? Because they literally just bounce. They're waves that bounce forever. So how do we deal with it? So the squeeze theorem is a really useful tool. All right. So this is how we did this with functions. So let's look at the conditions to use it for sequences. Okay, and it's pretty similar. So let A, B, I know, it sucks, right? C, B sequences where all the terms in A are less than the terms in B are less than the terms in C. So there's a little extra caveat here. It doesn't actually have to be true for all values of n, okay? It has to be true for all values of n where n is greater than or equal to capital N. And what we're saying here so n is some known value. So I'm actually going to show you an example in a second where we actually explain where this can happen. So sometimes you have two sequences where one of them is bigger in the beginning and the other one is a little bit smaller for the first handful of terms. Then suddenly at some known index, the other function overtakes the first function or sequence, and it's larger till all the way to infinity. So because we only care about the behavior of these sequences at infinity, it's okay if things are a little wonky at the beginning. We just want to know what's happening way, way, way down the line. So if it's true for all n, that's great. If it's always bigger, that's perfect. But if it's a little dicey at the beginning, but you can find that value in for after that they cross paths, you're great. So I'm actually going to show you an example where we actually see a function that does that, and it's kind of obvious what's happening, all right? So, but before we get there, let's look at some examples that we can use, all right? But let's finish this theorem first. Okay, so we've said that it doesn't have to be true for all n, just n greater than some known value n, And we would say, well, then the limit as n goes to infinity of a sub n is bigger, or excuse me, less than or equal to the limit as n goes to infinity for b of n, and less than or equal to the limit for c of n. So just like with functions, the limit preserves the order of the inequality. And then I think it's obvious where this is headed. If the limit of a sub n equals the limit of c sub n, then we've squeezed the middle function sequence, keep wanting to say function today. We've squeezed the sequence in between those two values, so it also has to be L. So what can be challenging to do these problems is, what do you pick for your bigger sequence, right? And what do you pick for your smaller sequence? And when do you use this to begin with? So there are some tells, right, in the equation that'll kind of tell you when you're in a situation that you might want to use the squeeze theorem. So let's look at an example. We're going to look at a couple of these. So the first one I mentioned was trig, okay? And so the reason we need the squeeze theorem here is because we're looking at the limit as it goes to infinity. So if you know that that numerator is a wave, right, you can't even get in a L'Hopital situation here, because the numerator will never be less than 1, or never less than -1, never greater than +1. So if we try to look at the limit, we're not going to be able to do it. So I need to pick a function that's always bigger, and I need to pick a function that's always smaller. So since this is in the numerator, I can say, well, cosine will never be less than -1. And it will never be greater than +1. So I can literally sandwich it in between those two functions. So is everybody clear on why this equality works? Okay. Now, taking the limits a snap. And the idea here too is you want to try to choose things that you kind of know the answer to. I mean, that's kind of the point of this, is like we don't just want to pick something, we want to pick something that we can actually evaluate. So the limit of 1 over n as n goes to infinity is 0, and the limit of -1 over n as n goes to infinity is 0. So this is 0, this is 0. We've sandwiched cosine of n over n in between those two values. So now I can just say a sub n converges to 0. So the values of cosine, because there's no amplitude in front, right? The values of cosine are just always going to be between -1 and 1, right? If you actually draw a cosine wave, it just bounces back and forth between -1 and 1. And that's why we can't evaluate it as we go to infinity, because we don't know where on the wave, where does it really stop, right? So what we've said here is, well, the numerator can never be greater than 1, right? And the numerator will never be smaller than -1. So I literally just replaced cosine with its maximum and its minimum value, and that gave me the maximum and minimum function I could sandwich it in between. So we do the same thing for sine, right? If sine's in the numerator, you can go -1 to 1, right? Okay, everybody good? Switch paper? Okay. All right, so let's look at another example of when we might want to do this. So here's another tell in a problem when you might need to use the squeeze theorem. When you have negative anything raised to the n. So we know that even values of n make that number positive. Odd values of n make that number negative. So these, Here we go. So this function is going to alternate between positive and negative values. So we actually call this an alternating term. So if you see a sequence where the values are going positive, negative, and you want to write the equation for the pattern, you have to put an alternating term in there so that way you're getting that happening to you. So just like with cosine and sine, well, I know that that value will always bounce between -1 and 1. So I can literally rewrite the function like this. So that -1 will never be less than -1, and it'll never be greater than +1, but I can't actually take the limit of the original function in its original form because it's constantly going up and down. So now, of course, just like in the last problem, if we take the limit, we see that we've just sandwiched this guy between 0 so this converges to 0. All right, so let's look at another example. And we're actually going to play with this guy quite a bit. We're going to do lots and lots of examples with 2 to the n, or 1 over 2 to the n. So one of the things I like to do is I like to show you the same sequence or the same series when we get into those again and again and again, especially the really robust ones that can withstand lots of different tests. Because even though we know the result, and you might just say, well, that limit's easy, you could just say it's 0, which is true. I want you to see, like, if I'm showing you lots of different techniques, I want you to see if I give you the same function and we use a lot of different techniques to get to the same answer, I kind of hope that you can see, oh, well, this is what the technique involves, you know, versus this is just this random function or this random sequence. So in this case, we can actually use the squeeze theorem to prove this, right? But the reason I picked this particular one is this is an example where, excuse me, we're going to see that I'm going to compare it to something that may not be greater than it when they're small, but there is a value in for which it overtakes and it gets bigger. So if we look at this guy, right? What is an obvious choice for the lower bound? What can this guy never be? 0, right? This guy can never be equal to 0, and more importantly, this can never be negative. So if you have something that's always positive and you're pretty sure this thing's going to go to 0, well, then you can literally use a constant as one of your bounds. So we can say, well, I know that 1 over 2 to the n is always greater than or equal to 0. And if I want to pick something larger than it, well, a fraction with a smaller denominator is bigger than a fraction with a larger denominator, right? As long as their numerators are equal. So I want to compare it to something that I know the limit of, but I want to keep the numerator 1. So that way I know if I just get a bigger denominator. So I'm actually going to use n. Because we've already discovered from the limit we did earlier where we did n squared over 2 to the n, we already saw that 2 to the n grows faster than n. So if n is a smaller value, then 1 over n should be bigger than 1 over 2 to the n. Yeah.
If you had a numerator for the 2 to the n,
I would have kept the numerators the same.
Gotcha. So you'd
Yep.
say 1 and 1 to whatever.
Yeah, if I'd have had like a 3 on top, I would have called it 3 because I want to make sure that I know that this thing is truly greater than or equal. All right, so this isn't true for all n. Oh, actually it is true for all n, my bad. That's right, I have another thing later we're gonna play with. All right, so this is actually gonna be true for all in, but just to prove it, let's make a little table. So if you're ever not sure, all you gotta do is compare some numbers and we can check this out. So if n is 1, then this is 1/2, and this is 1. 1 over n is definitely bigger. If n is 2, this is 1/4, and this is 1/2. 1/2 is definitely bigger than a fourth. If we grab 3, we get 1/8 over a third. A third is bigger than an eighth, and we'll go one more. We'll say when this is 4, we get 1/16, and we get 1/4, and 1/4 is bigger than 1/16. So I actually know this is true for all n because from every n beginning from 1, and I can see this pattern emerging, right? 1 over n is going to outpace 1 over 2 to the n. So now that we've confirmed that this is a valid inequality, we can simply take the limit. So clearly the limit of 0 is 0. The limit of 1 over 2 to the n is got to be less than or equal the limit of 1 over n, which is also 0. So once again, we've shown, oops, that this converges to 0. So this is another valid known limit. So this is going to be another one of those general limits we're going to just be allowed to cite when we see them. So this is true for any constant c that's not 0 or 1. Because 1 raised to the n is just 1, and you would get 1 over 1, and that's not 0, right? And then you clearly can't have 0 in the denominator, so we would just say for any constant c we see. So if you're doing a problem and you got 1 over 3 to the n, you can just tell me the limit's 0. Like, you don't have to go through and prove it, but you're wanting to see that you can prove it using the squeeze theorem. Yeah?
So, the left side of the squeeze theorem chose 0 because 1 over 2 to the n.
Yeah, I chose 0 on the left because 1 over 2 to the n can never be negative. So I knew it was bound on the bottom by 0, and I was pretty sure that the limit was going to be 0, so I wanted to pick something on either side that would turn into 0. So when you use the squeeze theorem, you kind of have an idea of where you're supposed to be headed. The only problems where you just kind of dive in and see what happens is maybe when you've got that -1, or you've got a cosine or sine function, you might immediately replace them with 1 over, and then later on when we get to some more complicated stuff, we may have to do a little bit of additional manipulation. But these are kind of the 3 obvious choices when you're trying to apply the squeeze theorem. Yeah? Anything else? All right. All right, so we're about to look at